Hello everyone, welcome to the second day of our workshop. First, before I begin the workshop proper, I wanted to say that apparently there's problem with dependencies and with the version of Qiskit, since the version 101 has some functions, the version like lower than 101 has some functions which are deprecated. And so, for example, the execute might not work. I'm using the version 44 because that's the version that's used in the notebooks. And to be honest, I came back home just before the workshop. There is a very handy site for this sort of thing, which I will show to you, or rather link it. For example, in important links, where you can check what you need to replace your function with. But because that's a problem in the notebooks, after the workshop, I will publish just an example task that we did yesterday, but with the functions that will work in 101. All right, let's remind ourselves what we did yesterday. First, we reviewed some basics and reviewed the Qiskit, which is the framework in which we are working. Next, we looked at classical gates and how to implement them in a quantum way. We learned about phase kickback, which is a very interesting and important phenomenon, which is used in many quantum algorithms and which we will see today still. And finally, with the Deutsch algorithm, where we saw how the oracle model of computation can be used to show some sort of quantum advantage. But if you remember from yesterday, it's likely you didn't have the time to watch the recording, so that's completely all right. But Deutsch's algorithm, the only thing it does is instead of 2 evaluations, we're doing 1. And this is not a big gain. We'd like something, for example, scaling with n. So if it was n instead of 2n, that's already better. And this is what we'll learn today. But also, very important things to note, because they will be repeating time and time again, is what a Boolean function is, what an oracle is, the general way the algorithm looks, just the general of what we're using, that we're using nodes, Hadamard, and the unitary gate and measurement, and phase kickback, which is important. And well, the 2 algorithms we'll be doing today are fairly short, and the notebooks are short, so there's a chance we'll end earlier. And you might think that they're kind of similar and not that important. I think there is some big value other than showing some bigger advantage. You'll see how to play with the different building blocks that we discussed and I mentioned a little bit before. And this is important because if you learn a new quantum algorithm, you can just look at the algorithm, implement it, it will work. However, the goal of this workshop is to show you how it works. And I think that that's a very interesting thing to know, even if you don't plan on continuing your journey. Very often people ask, well, what is a quantum computer? Well, how does it work? How is it faster? And knowing that, I think, is interesting in itself. Well, we can start. First of all, we will do Deutsch's algorithm. As you can see, we have Deutsch in the title, so we might see some similarities. So let's see what we remember from Deutsch algorithm and what's similar. We have a function, And the difference here is n, because if you remember, it was from 0, 1 to 0, 1. And we had, maybe one use the arrow, and we had 4 possible functions. All right, and if we have f 0, 1 and 0, 1, how many possible functions are there? So we can have, if our n is equal to 4, we have 0, 0, 0, 0, etc. until we get 1, 1, 1, 1. So does anyone have any idea? You can write it in chat. Yes, exactly. It will be 2 to the power of n. Important thing to note here is that is an even number. So 2 of n possible functions. All right, so we know what it does. If it doesn't, then let me know. And so we have an n-bit string. We're mapping it either to 0 or to 1. So each one of these, we're only mapping it to 0 or 1. So remember, it's not another string of n, it's just 0 or 1. So f is constant if it maps every string of length n to either 0 or 1. So here's an example of a constant function. That's what we know a constant function to be usually. So in case of bits, it's similar. We have to have either all zeros or all ones. And we can achieve this because this is even. Oh, no, this will be another point. So if a function is balanced, then half of the outputs have to be 1 and half 0. And that's where we need the evenness. All right. What is our problem that we're trying to solve? Well, it's a generalization of the Deutsch problem and the Deutsch algorithm, as you will see. So we're given it as an oracle, and we want to decide whether it's constant or balanced. Now, a lot of things won't change, which we like very much because we wouldn't like to do a lot of work figuring out other solutions. So for example, if we want to implement the unitary gate, if you remember, this is what it goes to. It's from x by the unitary gate x not changed and y so that we can get the result. But when x is an n-bit sequence, so for example, x is, well, x1, x2, x3, etc. until xn, and y still will be a single out qubit just because the range or the output is 0 or 1. So this will apply. We're using the same model here. That's all right. And we're glad about this as well. We can still use phase kickback. Here in this case, just to determine, if you remember, the eigenvalues were either 1 or -1. So this is what we can get kicked back. Of course, if we get -1 to 0 is 1, and -1 to 1 is -1. So here we'll get phase gain back. That's why we're marking it this way and still have x and minus. Now we need to represent the quantum states of an arbitrary length, the arbitrary length being n. And this is the standard notation that you will see in the literature. So this essentially you can think of it as a sort of power, but for the tensor product. So we're just putting 0, tensor product, 0, etc. n times. And for quantum operators, we can do the same thing. That means we'll have this operation n times. All right. Now this is a very strange notation, which is, I would say, not intuitive. But we can use x being in natural numbers as the binary representation of the number. So for example, 42, we need to know what 42 is in binary. Well, fortunately we know. And so then if we see this, we have to calculate binary representation. And then count the bits. And this is what it will be in 6-qubit register, but of course if you have an 8-qubit register, you can put zeros in front. Next, let's look at Hadamard again. So if we're applying Hadamard to state 0, then we're getting the state plus. If we're applying it to state 1, we get minus. Now, let's have x1, which can be either 0 or 1. And consider the expression where we're putting the operator, the Hadamard operator, onto the state x1. We can write it in the following way. What is this and why is this? We're essentially combining these two because it can either be this version or this version. And what do they differ by? Only by the sign. So as we saw before, the easy way to merge these things if we use the power here. And this is what we're doing. So this is either plus or minus. Next, we can simplify it even further or complicate it depending on how you look at it. So we're just writing it as a sum, which not exactly necessary, but it's a possible representation here. And what we're doing here, well, let's just write it out slowly. So first z equals 0. So this will be 0, so this will be 1, state 0. And then z is equal to 1. And then x1 is x1, we don't know, and z is 1. So we'll and z, which is 1, which is exactly the same what we had here. So this is a representation which we'll use. Now we can apply Hadamard to an n-qubit register, which we have been doing because we've been applying Hadamard to all like to all qubits before. So if we apply to the operator 0, then the only thing we need to change in this representation is, first of all, to get this state, you will be multiplying 1 and by square root of 2 of n. So here we have the possibilities. Next, here we have a sequence again. Nx. And here, this representation is useful. So that's why we needed to go through this, which is not necessarily needed here. Now, what if we don't have 0, we have any state? So we have x. So first we have some state. So this, we already saw what we can generalize it to. So that's what we're using. And we're doing it n times. And how do we simplify it? Well, let's see. Here, we're multiplying 1 divided by the square root of 2. So we'll have the n here. Next, we're summing. The sum is the same. So we can bring everything under one sum. And so here, well, important thing to note is x is x1 up to xn. So next we're using the whole x here and the whole z here. So the whole sequence of this, because we had x1, x2, etc. until xn. And well, xz is the bitwise and operation modulo 1. We can quickly write it out. The bitwise AND operation. So if we have 0, 0, here it's 0, here it's 1, we're adding and modulo 2 is 1. Similarly, here is 1. Here we have to use the modulo, it will change something since we get 2, and this will be 0. So x times z, if we want to show it in this representation, we'll have to use the sum again. All right, and next, I would like you to try to utilize these tricks to calculate age tensor product 4 to state 15. So you'll have to use all of this that I just explained. And we'll give for it 5 minutes, but I will again pause the task, and I think it might take a little longer, but we'll see. So first, With this specific task, I will just show the result. However, if you have a different solution, then you can post it on Discord, for example, on the lectures channel, and then we'll check it. Maybe not now, but definitely at some point. All right, I don't see anyone needing more time, so we can proceed. This is using just all the tricks that I showed you, but I know it might be tricky at first to know when to apply them. What is 15 in binary? It's a convenient number. Oh, and is needed. So I'm marking it according to this definition. Next, we can already write it as a sum that we had here, or in a similar way at least. So first, let's write just if you applied Hadamard to it. We'll either have 0 or 1. Minus 1. And now we're using this here. Z1 state. And let's simplify it a little bit. We only can have it 0, 1. So there are two options. So we can write it out. First option, Z1 is 0. So this will be 0. This will be 1. We get Z1, but it's 0. So we get state 0. Next, Z1 is 1. This will be 1. So this will be minus 1. This is 1. So we're getting minus 1. And do not remember this. We're applying it to 4 qubits. So in this situation, to achieve this, I will now write the Hadamard gate in a way that might be unfamiliar to you. But we'll have ones. Usually we start with zeros and apply X gates, but I think we can skip it here. And we'll apply the Hadamard gate. And we're getting minuses. Which I think, if you know how Hadamard gate works, it makes sense. That's why we're kind of juggling here the notion of applying a gate to a single qubit and applying them to all qubits in a way that they form a sort of composite system. So here, for example, we're using more the notion of just putting it on one qubit and then just using it 4 times. Now, this task 2 will skip. Now let's discuss some things. First of all, we have the problem before us. So how many times do we need to use the oracle if we're solving the problem classically, in the worst case? So we're deciding whether the function f01n to output 01 is constant or balanced. First of all, if you don't know the answer, we can think about what will be harder to check, if it's constant or if it's balanced, or how many times we need to check. Let's say, if you know the answer, you can write it in chat, of course, or say it out loud. So first, we have a function of n equals 6. No, that will not work. 8. And next, we have an oracle, and we ask it, what is f? All right, maybe that's a bit too much. Let's stay with the 4. We ask the oracle, and so it says it's 0. Now, that's the first query we make. We make the second query. Let's go in order. And now, she can give us two options, 0 or 1. Could you please write in chat um, whether any of these satisfies us? Like, do we end the algorithm here? Well, yes, the numbers might be a bit wrong because, as you know, we'll have many more options here. So we'll have 0, 0, 0 until 1, 1, 1, 1. So we'll have to make more queries. So if we get 0, that doesn't tell us anything. Let's say it just doesn't answer. But in the case that we get is 1, well, now we know that it cannot be constant. So you can think of an easier example, maybe like we did 2 qubits, maybe with 3 qubits. How many times do we need to check it? It will be expressed with n as well. So the worst case. Very good thinking from Azad and Dominica. You're a little bit off, but the thinking is correct. Essentially, imagine that we have some n, and we're asking the query. So we're asking first query, second query, up to n half of n queries. And we've been getting only zeros. Now what we have left is the n divided by 2 plus 1 query and some other queries until we get n. So that's half of our queries. So, oh yeah, I do see that you added the one. So yes, that's correct. Sorry, Azat. And so now we still don't know because it might be constant, but if we get all ones here, we're very, very unlucky. Then in that case, it will be balanced. So exactly the answer here will be 2 to the n divided by 2 plus 1. Okay. How many times do we think we'll use the Oracle F while solving it on a quantum computer? I would like to hear 3 guesses, which can be completely just based on your intuition or what you think, or think of it as betting on how good a quantum computer is. So how many times do we need to do these queries to answer our question? So I would like to have 3 bets here. Even if you're not really basing them on anything. Well, we do need to proceed. So let's say first bet is 1. Second bet will be, let's say, 2n divided by 2. And third bet will be 10. Just because 2n, we have 2n. 2n. And n minus 1. Okay, okay. Let's, the 10 is a little bit absurd, so we have n minus. We'll come back to it. So the algorithm. We're just given the circuit. And I hope you notice some similarity. This is just the formulation. I trust that you can read from the diagram what the algorithm is. But of course, first we have n plus 1 qubit. This is the 1 qubit, this is the n qubits, which is right in this notation. So this is not 1, just all of the n ones. And this is our x, and this is our y. So the similarity I hope you're noticing here is to the Deutsch algorithm. Let's compare them. We have the NOT gate here, 2 Hadamard gates, I'm reading the question. You expect the output. Okay. All right. You see, this will be the fifth answer here, which is very optimistic. Oh, the one was already here. But we'll just leave it. Yeah, so we have the Hadamard gates. Just here we have n of them. We have the unitary gate, and finally Hadamard gate and measurement. Notice that again we're not doing anything on the y, or rather we're doing things and they are important, but we care about the measurement from up there. So this is the only difference. So we're in a perfect position for designing a quantum algorithm because we have a very simple, let's say, toy problem, which is Deutsch algorithm. And then inside that algorithm, we're using some properties. For example, phase kickback or the oracle. And additionally, we have a circuit that we're designing based on the algorithm we made. And it's a lovely thing when that happens, when we're trying to generalize it into a harder kind of problem. And we can use all the properties and we can use the same circuit, almost the same, like the same in structure. Now we're going to perform an analysis. This is just the to here. And let's go do some more mathematics. So now we're designing a circuit with n inputs and 1 output qubit. First state, we have 0n, and we have the second 0 here. We're applying the NOT gate to the output qubit, so we're changing it to 1. Next, we're using Hadamard on the output qubit, and since it was in state 1, we're getting a minus. So also we're applying the Hadamard gate to the first n qubits, which again we saw previously. We remember why the n is here and we remember what this means. So that's because we're using it n times on n qubits. This is because we're just summing it over all possible sequences. This notation also depends on the value of f, whether it's 0 or 1. And finally, we have the output qubit. Finally, we have to apply UF. And we're using the sum notation again. Yes, and this is an important term, equal superposition. If we have the sum of states, if we just write it all out, this is called an equal superposition. So now we don't care anymore. The output, we don't care about the output bit because the qubit because it was used and we're not doing anything with it. So let's focus on the input qubits. And what we're writing is the same thing, just without the output qubit. Next, what do we have? Applying the Hadamard to each and then measuring it. So let's apply Hadamard first with the notation that we're doing it to each of the qubits. X, which is a sequence, and we're using the notation here where nothing changes afterwards. So then we can calculate it. And here, let's see what's going on. We have two sums. So first, let's calculate it for n equal to. So it will be 1 divided by 4. And first, we're setting x to 0, 0. And then z is going to be 0, 0. Now, x bitwise addition z is 0. This will be plus. But notice that we're adding f of x. So here, well, I don't know what the f of x is, but let's say it's a constant function of 1. And so we would get minus 1, 0, 1, so it's 1, and z, which is 0, 0. Next, we'll be setting them. We would be setting them just until the end. So at the end, we have x equals 1, 1. No, x still is equal 0, 0. And z is equal 1, 1. I will not calculate all of it. I just want to show you how it works in general. So first, we're setting x in stone. We're calculating it for all possible values of z. So here for z being 1, 1, we're getting 0, 0, bitwise and 1, 1. So it will be the sum here. So it will be 1 and 1, so it will be 0. And we're getting the same thing here. So that's our first thing. And then we're setting x to a different value, setting it in stone, and we'll construct exactly something like this. And this will be the sum. And finally, parentheses closed. I just want you to see the structure of it. You can calculate it yourself, for example, for n equals 1 to see how it works. Now, we know that what the probability of observing a state is. It is equal to the square of its amplitude, or the module of the square, or square of the module, sorry. So if we have amplitude lambda, then this is the probability. the state. So if we have z, which we see 0 n times, if we replace z equals 0 in this sum, then the amplitude will be given by, so z is equal 0 to the n. And so the amplitude now will just say f of xy, because z is equal 0, so this will cancel out. And here is the state. So we're looking at the probability corresponding to the state, so we don't use it. And well, this will be the formulation of it. So nice. Now, if the function is constant, then this sum will add up to either 1 or -1. Let's calculate it for n equals 1. So first, x equals 0. And let's say f of x is again 1 constant. So it will be -1 and -1. So it's -2 divided by 2, so it's -1. And because the amplitude is either 1 or -1, we observe z with the probability of 0 n times, 100% of the time. And which is like the amplitudes of all the other states cancel each other, meaning we will have probability 0, meaning we won't observe any other states. So the probability of observing 0 n times is 0 if the function will be balanced. So that's, so 1 or -1 constant and 0 balanced. Are there any questions? So now, again, if you remember task from yesterday, if not, okay, it's okay. First, you need to run this cell to receive an oracle, which is just code in another file in the folder that you have. So it's called oracle j of n, and it will return a quantum circuit of f n plus 1 with n inputs and 1 output, and they're corresponding to either balanced or constant function. UF is oracle j of n. And the problem is that we have n equal 4, and we want to implement the algorithm that we just saw and analyzed. We'll have 5 minutes for it. But then again, if you need more time, we'll definitely have it. That's right, Richard. Thank you. Welcome back. We can get to some coding. We are giving a DJ circuit from Deutsche Josa, not the profession, which has 5 quantum registers, 4 classical ones because we won't need a measurement on our last qubit. At first, we need to apply gate not. Well, first, let's revise what we need to do. We need to apply gate not to the last qubit, then Hadamard's to all of the qubits. Next are oracle, Hadamard's to all the input qubits, and measurement to all the input qubits. So let me copy that. Next, the Hadamard's. Let's use range to so that I don't have to write that much. So it will be from 0 to 4. And now we can use the compose function, which is in the Deutsch algorithm notebook as well. It's what we used yesterday. Oracle J as the task suggests. And we'll put it on 4 qubits, so all of them. And then in case it's true, next we need to apply the H gate again, but now not to all of the qubits. Of course, if you do apply it here, it doesn't matter since you're not measuring, but we don't need to waste resources. Range 4, so from 0 to 3. And again, 0 to 3. And we can draw it. Where is this? Alright, we're including everything here. Okay, we have it. So we didn't use barriers exactly, but you see we're using not gate, the Hadamard gate on all of these. And next, we see we can look inside the black box at what the oracle is doing. And it is putting a CNOT with the control being Q0 and Q4 being the target. And then we again put Hadamards and measure everything. Now, if you can see whether the result was correct or not, you can just think about it. That's not an obligatory question. And next, let's see what we had. And this is the result. So 0, 0, 0, 1 observed 100% of the time. So here you'd have to work backwards a little from the CNOT to know whether it's correct or not. Now, task 5. Let's do task 5 as well. In it, you need to write two functions, which will balance n of n and constant of n, to randomly generate quantum circuits. So far, we have been given it, but for testing things and for understanding it thoroughly, I think it's good to write it. And we'll have n plus 1 qubits that will implement the function that we all know by now, that is either constant or balanced. And qubit n is the output qubit. Again, 5 minutes. We can continue. Now we can come back to the question I asked before. What happens with this oracle? We're getting one CNOT where we have the control on qubit 0 and the target is the last qubit. So, and finally we get the output, which is just the 4 qubits. And in that case, what happens, note the cascade order, is that got switched to 1. Meaning that got switched to 1, meaning we had a 1 previously. We had a 1 here. And then we got it out of the superposition. So that's just one thing you can notice what is happening. The constant function will be easier to write, so we can start with that. So what happens when the function is constant? F of x, for example, will be equal to 0. We have to generate the constant circuit. If we can go here, do we have to do anything here to change it? So our algorithm is here. We're applying the UF. So if it is 0 to n, the function is constant if we get all zeros. All right, but we would have gotten zeros anyway, without changing anything. If it was constant, if f of x was 0, then we'll get zeros. And that's meaning we don't have to do anything actually. But now the other option, where f of x is equal to 0, if x0, so the first qubit is, or just I will write the first qubit, will be equal to 0. And that would mean that x1, second qubit, will be equal to 0 as well. And similarly, if it will be equal to 1, if the first qubit will be 1. And here we have been giving an answer in a way, or one of the answers. We had to, because we got this version, we didn't have to think as much, because when you're getting a constant function, you don't need to do anything. If you're getting a balanced one, we don't need to apply a CNOT. So we need to apply a CNOT where control is the first qubit and the target is n, just as we've seen here. CNOT, the control, and then n. That's what we think might be good. Let's see. So n equals 5. So here we're trying to see the balance function and we're drawing the output. So if it's balanced, we're getting a CNOT, which is what we got here, which is good. And if it's constant, we're not getting anything, which is also what we wanted to do. So we essentially just implemented what was going on in here, in this black box. Now for the end of analyzing Deutsche, I will switch back to OneNote. So Deutsche algorithm is very interesting because we are able to solve the problem making only one query. Where were our bets? Here. So this one is correct. Only one query. So it seems very, very good. Yeah, and here we can see how good the Oracle model of computation can be. If applied correctly, it really speeds up our quantum algorithms. But now we meet another point, and here I can talk about just the metaphysics of quantum computing a little bit, since in pop science very often it is claimed, or even science, that we have achieved quantum supremacy, which would mean that, yeah, we have the problem that quantum computers can solve quickly and classical computers cannot solve it as quickly. But here we needed to be very specific. So very often it so happens that the company would claim that we achieve quantum supremacy. If we and we have this problem that we're solving. If we solved it classically, it would take like let's say 10,000 years. But if we want to solve it in our way, we just need to wait one day or even sometimes 10 seconds. And very often this claim is correct because, well, they have to get through peer review with their papers. The problem is that in that case, unfortunately, it happened quite often. It has been happening quite often where someone else will come forward and say, well, here's, you're correct. However, there's another algorithm that solves the same task in like 20 seconds. It just, they showed one of the possible algorithms. So we showed basically the worst algorithm, the worst sensible algorithm, but we have a probabilistic algorithm, so using randomness, which will solve the problem making only three queries. And here we don't see that speed up as significant. So that is of I think that it's useful to pay attention to. So the caveats, well, what we've been solving is named Deutsches problem in the simplified version in Deutsch algorithm, in the full version in parse type in Deutsch JOSA. But it has no known applications in the real world, which well, we would like to have. The method of evaluating a function. Yes, if you're comparing algorithms and you have a completely different method of evaluating a function, some say that the comparisons may be invalid. And yes, if we choose a random X, we can solve it using just 3 queries. So that's it for Deutsch Jasa. I think we'll take a 10-minute break until past, and I will see you then. And we're back. We can go to another example of an algorithm in which you will use the oracle and the general model that we've been using so far. But we have a different problem now, a little bit different at least. So let x dot s represent the inner product of the bit strings modulo 2. Now, I think I'd like to write you some properties of that, since you might be unfamiliar. So let's just make some space. So the bitwise dot product, inner product, if you want to call it that, xy, because you can calculate it in a way that we'll see in a moment, but you can also see it very quickly. So this tells us or answers the question. So these are bit strings. And we're just checking how many ones, meaning the ones are on the same position. Now the interesting property of that is that if we're using x dot x, since all of them will be at the same position because it's the same string, then it will just tell us how many ones in x. And then if we have what we will be using, so modulo 2. Okay, so this will tell us whether the number of common ones odd or even. So we can take a lot out of this operation. But how do we use it? For example, we have two bit strings. We have x and s. So we're having 1 and 1. Yes, this one is in common. 0, 0, not a 1. 0, 1, not two ones. 0, 0, not two ones. Meaning we have 1, modulo 2 is 1. Now, what is the problem? We have an oracle function. Again, a well-known one for us, which will be designed as f of x is x inner product s. And we want to find the secret string or the sequence of bits of s. So we don't know what s is. That's what we're trying to find. And yes, this is another kind of problem that I mentioned before, that first you come up with a solution and then you look for a problem to fit that solution. But in terms of showing you how these kinds of algorithms work, it's good because it's very simple. When you look at algorithms like Shor's algorithm, it consists of many smaller algorithms. So again, we see the block structure. And inside those algorithms, they also use different blocks of what we can do with quantum computing. So just nice to, if you start noticing some small similarities, I think that's very good. So we need to, let's go through an example. So n is equal to, and we just assign some numbers. zeros or ones to the output. Now we see here that S is 0, 1, and to check that it would be correct in that case if we guessed S is 0, 1. So not anyone in common 0, 1 in common, so 1, 0 in common 0, and again 1 in common, so 1. So we don't need to use the modulo 2 here. And we can see that it's exactly what we've seen with the outputs of the function. And now the unitary operator will take a little bit of a different form, but that's just because that's f of x. So it's just a slight difference. So task 1 is using how many queries can we solve it classically. And then again we'll place some bets. I'm giving you a couple of minutes, just like 2 minutes for thinking. Okay, so classically, again, I can show you how I can achieve this. It's a fairly smart way of showing it. So here, very often in linear algebra, if you want to know some structure, or if you're looking at some problem, it is very useful to just use, um, for example, let's take n equal 4, and let's use a set. So we just want to know about this position and then this position. I'll show you why in a second. All right, so that's what we have. And now I'm telling you about this being useful in algebra because this is where your intuition might come from. If you don't have it, that's also okay. So what will it be? So it will be some S1 because S will be 4 things. You can assign them names. Okay, how many common ones? Those are all zeros, so there's no way any of these is 1 because they won't be common ones. Here it might be, so these will cancel out. We might just write this. In the end, it will just be S1. Similarly, Here we'll end up with just S2 because these will cancel. And let's just write the answers for the rest of them. This will be S3. This will be S4. So that's an example of, so what do we need to evaluate? Here we have n equal 4, right? So we have 4 places. And for this, we need to know S1 to be able to evaluate it. For this, we just learn S2. Through this, we learn S3. And through this, we learn S4. Which means that we need to check 4 times. And if we need to check 4 times, generalizing it n times, classically. Now, you might see, it might seem like in many places we're taking some slight shortcuts. For example, when I tell you just, it is just n times classically. You might ask why? Is there a better algorithm? But for this, you need to submerge yourself in papers, and an answer to that question would be if I knew, just telling you about all the different papers with different algorithms and why they didn't surpass this. So how many queries do we think the quantum computer will need? And again, I would like 3 bets, please. All right, since I'm not seeing any, I will just say 1 and divided by 2 and n minus 1. So next, what can we say about the f function if s is just zeros? Well, if s is just zeros, then how many common ones can there be? None, because all of these will be looking at 1 0 or 0 0. In both these cases, they are not common ones. Okay, now we're given the algorithm. Again, you can see the similarities probably. So we have n plus 1 qubits. Here we have n. I will change the color. And here we have just 1. First, we're setting the state of this to minus. So here we'll have minus. And we're putting all of this in an equal superposition with Hadamard's. Next, we're applying our unitary operator. Again, the Hadamard's, but not on the target qubit. And finally, we're measuring all of those qubits to obtain S. Why does that work? So first, after the initialization, we'll get the same state that we saw not long ago. So again, 1 divided by the square root of 2 to the power of n. And then we're getting a sequence of zeros and ones, summing over it. And we'll have x's and always minus. The minus is from the last qubit here. So this is the state that we have after applying the Hadamard as well. Next, we can apply RUF, and we're also getting rid of the last qubit, we don't need it. We're getting a state where we will either see a minus before it or a plus, just if you remember the base states, for example, for 2. And here we can have plus or minus. Here, 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 here. We can just have plus or minus. That's where this comes from. So we already applied all this. Now, since we have f of x here, we know what it's defined as. It's defined as x dot product s. So we're just changing this here. Previously, we saw what the result is of applying the Hadamard n times to x. So again, to a string of bits. And for this, we can just write it x, z, and then state z. Now, very important property here. So the h gate is its own inverse. And so we have something like this, that if we apply the Hadamard gate onto A, we get some state B. And what we can rewrite it as is we can multiply it both sides here. This will cancel out. Here we're getting the Hadamard gate applied n times and then just switching sides to illustrate it. And so what is 3 again? Since we can just put an output like that, so we get psi 3 if we apply Hadamard onto S. So we know what that is. We know what that is. That's what we're looking for. And so if we put Hadamard again, so again, as if we switch sides using this property, we'll just get, so we're applying the Hadamards again, psi, and so here we just get S, and this is from this property here. And so we found what we wanted, so the string S, and we measured the first n qubits, and on the first n qubits, we'll see the string S with probability 1. So again, it will be this answer, which our optimism is paying off for now. Next, the penultimate task is having been given an oracle, which is designed specifically for Parseval's-Rani algorithm, it will construct a 6-qubit oracle, meaning S will have length 5 because the last one is the output qubit. We want to construct the circuit essentially implementing the algorithm. But we know what happens and how that happens, and also we have the algorithm here. And we can write it again in a very similar way. So for that 5 minutes, This time I see more people are still working. Um, if the number gets lower, if you change it to the full moon, if you are done with the task, then we can proceed. And until then, we can wait just about 2 more minutes. Okay, I think we can proceed. This is a similar thing to what we did previously with Deutsche Josa, and the solution is also similar. What do we do first? A very similar construction, so NOT gate, Hadamard's, the unitary gate, Hadamard's measurement. Not on the target qubit. Hadamard on all the qubits. The oracle. Next, Hadamard again, but we don't need to put it onto the target qubit because we're not measuring it. And then we're drawing it. What do we have? A very similar structure in terms of the oracle, but now we're using more CNOTs. Is what we're doing. And all right, and let's see what we get. Our secret string is 11010. And I think it will be correct in that case. I hope you got something similar. This was just, I mean, the gates are simple. It's just looking at the oracle and seeing that it's will be correct. You might have asked the question, I mean, yourself a question. Why, how does it work that we're not measuring the last qubit, but we're using CNOTs where the controls are on the qubits that we measure, but the target is on the qubits that we don't measure? And the reason is because we're in the equal superposition. So that's the reason why we are able to do all this. It's it's as if you have some states and you're pulling them together and making them dependent on each other and changing with each other. And you can harness that power to do some operation that will result in a few of those qubits changing. So you can think of it as the heart of the solution to this. And next, we have our last task for today, where we are given an S, and we want to design an oracle again. What you can do is you can run this multiple times and see what you get. Try to see what the result is, and then think about it. Um, well, it's applied to all of them. As you can see, the oracle is just a box working on this equal superposition of all our states. And we're getting the oracle from another file, so we don't need to implement it, but we would like to. We'd like to understand how it works. I hope this answers your question. Now then, we can have 5 minutes for this task. Yes, it's for all qubits in that case. If you see something like that on the circuit, that means it's for all qubits. We can proceed to the final task for today. I think here, better than Barnsley Bazirani, um, we'll be able to see why we get the C-notes. Let's analyze this example again. What we're getting is the secret string S being 11010. So where do we have the chances of getting common ones with any other X? Only on S1, S2, S4. And, or rather, well, we're numbering it from 0. So this would be 0, 1, and 3. However, we're ordering from the back because cascade order. So 0, 1, and 3. So why are we putting the C notes? We're putting the C notes to condition our output based on where we have the possibility of getting the common one. Now, we're giving the string S being 0, 1, 1, 0. That's S0. We cannot have a common one. We can have a common one on S1 and S2. So you can already think about where to put the C notes. I have the circuit. Next, let's put a barrier so that it's nicely visible what we're doing. And then so here we'll have something, and then we'll have 4, since we're always putting it on the output qubit as a target. Could someone please tell me what numbers we'll put here? We won't be putting C notes on all of them because it would be the case with range 4 if we were doing a multi-control. If we were doing control 1, 2, 3, and then target 4, then we could use range 4. But since we're just looking here at where the common ones can be, look that we're putting just the normal C notes, one normal C note, and then second, and then the third in this case. So here we can have, I'm going from the back, but this is symmetrical, so we don't need to mind the cascade order, fortunately. So here we'll get 1, and the other one is just right next to it, so 2 is the correct answer. See if it works. Oh, we have to actually return it since it's a function. All right, we're supposed to implement a function. We don't really need to run it. So that's what we have. we can do and I guess Oracle. We're getting the circuit here. Display. Mm, let's see. Okay, thank you. I'm having multiple answers here. Oh, that's where the problem lies. Okay. Now, okay. Then let's go back. Well, here we go. Thank you. Well, we're getting the C notes where we wanted them to be essentially. I'm going here on 1 and 2. So this is the end, and we needed to make n queries. And well, we have the speed up, but it's not really exponential, but it's still much better than what it was. It's not exponential because we had n, which is already a fairly alright complexity to have. Alright, but we can go back to OneNote and just look through what we have learned today. We have learned two other algorithms where after Deutsch, we saw some interesting concepts, but we are not satisfied with the speedup it provides. Next, we saw Deutsch process, which is the generalization of the Deutsch algorithm. Hopefully, so this is important, I would say, and this is what you can get in the quizzes. So if you don't understand it, I think pen and paper is your friend to just write it all down. If you need to, you can even write it in matrices, if that would help you. And then we learned about the second problem, which is a little bit different, but where the circuit for the solution is very similar. So that's what we learned today. And with tomorrow, we'll end the conventional quantum algorithms part of our workshop. So tomorrow's we'll have Simon's algorithm, which is more complicated. We also should finish early tomorrow, but it will be more complicated, but we will be using similar tricks. And before we end, I would be interested to know what you think about these algorithms in terms of their usefulness. So, do you think this kind of speed up is okay? And do you think that it's good to show these kinds of speed ups even if they're not applied to other algorithms? And also, whether just putting all of them here in this workshop helps you understand them more, or whether it's just too much for you of the same thing. Oh, I'm very glad, Conrad. Yet, I think the similarity is good when you start introducing the variation to them in terms of learning. All right, I'm very glad that's the case, that they help you understand it better. It helped me understand it better as well. In terms of their practical use, we're at a point right now with quantum connected research where these kinds of examples and algorithms are important because they are the foundations of more useful algorithms that are being developed. Um, so all these building blocks that I was talking about, you will see them in more complicated algorithms. And that's how the field is also evolving by having more algorithms being more complicated, but at the same time better in terms of complexity or space. All right. In that case, thank you very much for coming. I hope to see you tomorrow for Simon's algorithm, and I wish you a good evening.